we have the solution. X of t equals a cosine omega t plus b sine omega t to the differential equation that represents the motion of a mass m under linear restoring force F net equals e to the equals negative kt. Okay, now we're going to put this in the form C. We'll choose cosine of omega t plus theta naught. We could also do the form C sine of quantity omega t plus theta naught. Okay, the Euler identity, e to the I theta cosine theta plus I sine theta. Now we just do the e to the I theta 1 times e to the I theta 2. And we write down what we have, and that's very straightforward. Now that is also equal, of course, by the laws of exponents to e to the I times the quantity theta 1 plus theta 2. And that is equal to what? By the Euler identity, plugging theta 1 plus theta 2 in for theta, we get cosine of theta 1 plus theta 2 plus I sine of the quantity theta 1 plus theta 2. Now you know from trigonometry that you have identities for the cosine of theta 1 plus theta 2, the cosine for the sum of two angles, or for the sine of the sum of two angles. Those are going to come right out here immediately. Okay? This has to be equal to this. So the cosine of theta 1 plus theta 2 is the real part of what we have here. And I've got a plus sign here. That should be a multiplication. Okay, this is multiplied by this. So what's the real part of this? Well, the real part of the product here is cosine of theta 1 cosine of theta 2 plus I sine of theta 1 times I sine of theta 2. But of course that's going to give us I squared times sine of theta 1 sine of theta 2. I squared is negative 1. And you should write this out. I mean, everybody should write this out at least 10 times in their life until it really becomes very second nature. And it's nothing but algebra 2 with a little bit of imaginary arithmetic, complex number arithmetic. We get cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2. Now mention we can also derive this in terms of angle trigonometry. It's actually much harder than doing it this way, but there are a lot of insights to be gained by deriving these equations the way they're probably derived, if they're derived at all, in pre-calculus or trig courses. Okay, anyhow, the sine of theta 1 plus theta 2 is imaginary, so that's going to be equal to the imaginary part of this product. And that's going to be, you have I sine theta 1 times cosine theta 2, and cosine theta 1 times I sine theta 2. So that's equal to cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2. So those are the identities for the sum of two angles. And if you had a difference, sum or difference, if it was a difference, then you'd have a negative on your theta 2, and the sine of theta 2 would be a sine of a negative, which is the negative of the sine of the theta 2, and that would change the sign of this, and it would also change the sign of this term. Cosine is an even function, sine is an odd function, so you can deal with that very easily. Okay, now how does that apply to this up here? Well, we need to think about that. So I'm going to pause for a second and write out a few more things. Okay, now this cosine of theta 1 plus theta 2 is going to become the cosine of omega t plus theta naught. And we're going to get the constant. I can't give you a good prediction of why that happens. It's fairly straightforward, but we just have to work through it to see. So what we want is a cosine of omega t plus b sine of omega t to be this side of the equation, and then this side is going to become a cosine of omega t plus theta naught. Now, how do we do that? Well, what we have is we have a times the cosine of something and b times the sine of something. Here we have something times the cosine of theta 2, something times the sine of theta 2. Okay? To get this into this form, we're going to let theta 2 just equal omega t. So we're going to have now a cosine of omega t and minus something times the cosine of omega t and something times the sine of omega t. Now, what are those somethings? Well, those somethings are cosine of theta 1 and sine of theta 1. We're going to have to figure out what theta 1 has to be in order to make this a multiple of this. So what we say is, okay, and I'm not going to go to all the detail in motivating this, just in the interest of time. We're going to say, okay, the cosine of theta 1 needs to be a over q. The sine of theta 1 is negative b over q, where q equals the square root of a squared plus b squared. Now, this is motivated by the idea that we have a coefficient of 1 here, so that the sums of these two terms, the sums of the square of these two terms has to be 1. Okay, just by your Pythagorean identity on sines and cosines. Okay, so what we get is, if we make these conditions, is that cosine of theta 1 plus theta 2 is then going to be, well, cosine of theta 1 times cosine of theta 2 is going to be a over q times the cosine of theta 2, which is omega t, and we got b over q here times the sine of omega t. We get a plus here where we had a minus here by letting the sine of theta 1 equal negative b over q. Okay, so we get this, and it's hard to argue this. It might be a little difficult to see how it's motivated. Now, if we let theta 1, well, theta 1 will be the arc cosine of a over q, possibly plus 180 degrees or pi radians. And as it turns out, if you think of the definition of a vector, and if you think of this in terms of a vector in direction theta 1, you see that theta 1 is going to be the arc cosine of a over q plus pi if b is greater than 0. So you can think about that, think about why that's so. If you make that assumption, or if you that's not even an assumption, that follows from this. Theta 1 must be the arc cosine of a over q, but that's only good up to 180 degree rotation. The sine of theta 1 equal to this tells you if you've got to add your 180 degrees or your pi radians. Okay, so what do we get? This becomes this. How? Well, I just multiply both sides by q, and I get q times the cosine of omega t plus theta 1, omega t being theta 2, and theta 1 being what it is. And that equals a times the cosine of omega t plus b times the sine of omega t. And that's what we started with up here. So using this identity, we've converted this to this form. So that's of the form c cosine of omega t plus theta naught. If we identify q with c, and the theta 1 we found down here with theta naught. So c is going to equal q, theta 1 is going to equal, theta naught, which is what we want, is going to equal the theta 1 that we get here. So this is one version of how we make this conversion. Now, it's actually easier if we already know it's going to have this form and try to prove it. We can use the double angle formula here. to convert c cosine omega t plus theta naught to a multiple of cosine omega t plus a multiple of sine omega t. And that's pretty straightforward, more straightforward than what we did here. In any case, that proves this. Now let's talk about what that means in terms of simple harmonic motion. Before we do what I just said, I'll also mention that we could use this identity with theta 1 equal omega t, and theta 2 being an arc sine, or an arc, a combination of an arc sine and an arc cosine, very similar to what we did here. And this identity could give us the form c times the sine of omega t plus theta naught. But if you run through that, you'll see the c has a different value, and the theta naught is going to have a different value. But that works out just the way we expect it to.